Hello, I'm Dr. Papuri Sheel, working as assistant professor in HNBS Jepularadi Engineering College. So in this lecture, I am going to discuss about crystallography and X-ray diffraction. Crystallography is basically study of crystals, whereas X-ray diffraction is one of the technique to study those crystals. There are other techniques also like a neutron beam, electron beam, but those are used for more sophisticated cases. Generally, for study of crystals, we go through this X-ray diffraction method. So what are the contents in this these are the outline of my talk. The first, in this lecture, we'll discuss only about the introduction. In the next lecture, we are going to discuss about cubic unit cell and their properties. Later on, Miller indices and how we find interplanar spacing. Lecture 4 will discuss about Bragg's law and X-ray diffraction. Introduction will give there. Then this lecture 5, Lowy powder method. These are the two methods of X-ray diffraction. We'll go in details about those methods also. And lastly, we'll compile everything with some problems related to crystallography and X-ray diffraction. So now, if we see here the introduction, see matter. Now, what is a matter? We all know from class 5-6 only we have studied matter under chemistry most probably. So matter is anything that occupies space, and it is made up of atoms and molecules. Matter can be of three types, that is solid, liquid and gas. In solids, atoms and molecules are closely packed, whereas in liquid they are loosely packed, and gas, it is like they are far from each other. So crystallography, crystals are actually solid. Now solids can be of two types. One is crystalline, other is non-crystalline. So non-crystalline is also known as amorphous. Now what is the basic difference between this crystalline and non-crystalline? In crystalline, the atoms and molecules are organized in some regular pattern. So there is a pattern how these atoms and molecules are occupied in the space, but in here no pattern is there in non-crystalline solids. Okay, so in this again, crystalline solids can be of two types. One is monocrystalline, other is polycrystalline. Mono means from the diagram itself we can have some idea, the figure shown here, that whatever the order is there in that crystal, it is same all throughout the crystal. But if we see this polycrystalline, in this we have some order in this region, some different order in this region. Order is there, but it is not same all throughout. There is some short range order here and there, they are different, so that they are known as polycrystalline. We know this mono, poly. Mono means single, all throughout the single order. Poly means multiple order will be there. So now we will basically discuss here about crystalline solid. We will not go on classifying whether this is monocrystalline and polycrystalline always. Wherever required, we will mention whether this is monocrystalline or polycrystalline. Otherwise, we will just say that this is crystalline in nature. Now next, moving to the crystals. Now when I say we study crystallography, how do you study them? It's like mapping of crystals. It's not because we map, that's why crystals atoms are oriented in that way. What we physicists do is, already there is some order, already there is some definite patterns of arrangement for atoms and molecules are there in those crystals. What we do, we just map them, how they are arranged in space. Is there any definite pattern which we can recognize? So what we do, we need some points in imaginary space, and we'll say those as lattice points. There will be infinite array of those lattice point, that is known as space lattice, or sometimes simply lattice also. So it is a lattice, it is infinite array in three-dimensional of lattice points. What are lattice points? These are just imaginary points where if we place atoms or molecules or groups of atoms, if we are placing these atoms and molecules identical every lattice point, then finally we are going to get the crystal structure. So lattice is not real, it is imaginary. We are mapping where this atoms and molecules, how they are organized, but basis is real. Basis is group of atoms, or sometimes it can be single atom also. Now which, if we place this atoms in those lattice points, we are going to get the crystal structure. Now crystal structure is very much real, but lattice is not. So that is about crystallography. Now we have this lattice is just imaginary points arrangement. Now we need to have some geometry connecting those lattice points. So we'll see that in our next slide. So what is crystallography? It's just study of crystals. How? By using some geometric structure. What kind of study do? We study the physical properties mostly. And what are the different techniques? We can use X-ray, electron beam, neutron beam, but most of the time in many of the syllabus you will see they are more concerned about the X-ray diffraction technique. We'll see that later. First let us focus on the geometrical structure, how we are forming the geometry. So next, moving on to the geometry part. Yes, unit cell is a geometrical figure, and the important word here is smallest. So any geometrical figure if you take, that is not unit cell. It has to be a smallest possible geometrical figure connecting lattice points. Lattice points are in space, imaginary points. Now we'll connect those lattice points and form a smallest geometrical figure. Now if we repeat this geometrical figure, then we are going to get the crystal. Here I have taken an example of two-dimensional lattice space. Two-dimensional lattice means it's growing in two direction only, either this or left and up and left and right. So you can say X and Y, two dimensions are there. Since we are taking lattice point in two dimension, our unit cell also will be two dimension. We are not going to get three-dimensional unit cell. So what kind of two-dimensional unit cell we are able to see here is A. A is a square like. B, C, these are not square like, these are rectangular like. So anyhow, how we got this A unit cell? We have connected 4 lattice point. So A is touching 4 lattice point. Is this all the single? If I take this lattice point, suppose 1, this is 2, this is 3, this is 4, right? Now if you see this 1 lattice point of unit cell A, is it completely inside A? No, it is not completely inside A, because if we repeat this A in X and Y direction, X also I am repeating, Y also I am repeating, then again here also we will get an A, here also we will get an A, and here also we will get an A. So you see this lattice point number 1, I have circled this one, it is shared with how many A? Altogether 4. So one lattice point is shared with 4 unit cells. So in one we have only 1/4 contribution. Out of total contribution, only 1/4. How many corners are there? How many lattice points are? A touching 4. So for A, what is the effective number of lattice point? 1. So what do you understand by effective number of lattice point? See, in A it is forming by connecting 4 lattice point, but all the 4 are not inside A. It is shared with nearby unit cell. So thus the effective number of lattice point is 1/4 contribution from one corner by total number of corner, that is multiplied by total number of corner, that is 4. That is true for A, that is true for B, C as well as D. But if we look carefully to E, E is connecting how many lattice points? 6 lattice point. Yes, E is connecting 6 lattice points. But you see on the corners, which are on the corner most, there are 4 corners. Yeah, so from this 4 corner it is again shared with 4 nearby unit cell, 4 into 1/4. Plus, why? Because there is this on the edge also, 2 more lattice points are there. It is shared with the top and bottom. This one also shared with top and bottom. So this is half shared up, shared down. This is also half shared up, shared down. So how much is the contribution from the edges? There are 2 edges and it is contributing only half. So 4 into 1/4, 1, 2 into 1/2, 1. So this is 2. So what is the difference between E and A? Or you can say A, B, C, D, all of them are kind of same in this case. The effective number of lattice point is 1 for A, B, C, D. But for E, effective number of lattice point is 2. So A, B, C, D, these are known as primitive unit cell, whereas E is known as non-primitive unit cell. This is true for 2-dimensional unit cell as well as 3-dimensional unit cell. Next, we'll in our syllabus we have to discuss about 3-dimensional unit cell. This is just for simplicity beginning, we are taking the simple example. Okay, so now let us move to lattice parameters. How we are going to find the lattice parameters? First we have to take a 3-dimensional unit cell. So here we are looking in this diagram a three-dimensional unit cell, how it is growing in x direction, y direction, as well as z direction. So there is one lattice point in this corner. Let us take this as origin O. Then another lattice point here. So how many corners are there? Altogether we can see corner 8 are there. So 1, 2, 3, 4, 5, 6, 7 and 8. Along x direction, from one lattice point to other lattice point, the distance is A. Along y direction, the distance is B. Along z direction, the distance is C. These A, B, C are known as primitives. Whereas, if we find the angle between x and y, y and z and x, it can be anything. It can be 90 degree, 120 degree, any other value. So these angles alpha, beta, gamma are known as interfacial angles. Altogether, this A, B, C and alpha, beta, gamma is known as lattice parameters. So lattice parameter is not only angles or not only the lengths, it is both. If we say primitives, then it is only A, B, C. If we say interfacial angle, then it is only alpha, beta, gamma. It is important to identify them so that we can classify different types of unit cells. Now let us move to our next slide, that is crystal system. Now, crystal system, how we are classifying crystal system? This is based on lattice parameters. This we have to remember, that we are classifying anything we classify, there is some basis, right? Good, bad, black, white, black, that's based on color, based on nature. So this is based on lattice parameters. So how lattice parameters? You see there is a relation between A, B, C and alpha, beta, gamma. If this relation changes, the system also changes. For cubic, all the sides are equal. And the angles, all of them are 90 degree. And similar way you will get tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic and triclinic. How they appear, you can see the geometry here for each of these cases in this table. There is also example given for each of these cases. Sodium chloride, if we say, so sodium chloride is cubic in nature. Now in this, as per our syllabus, we'll go through the cubic system. We'll go in depth, we'll do in-depth study of the cubic system. So you have to know what is cubic: when all sides are equal and all angles are equal to 90 degree. Who are these angles? These are interfacial angles. Who are these sides? A, B, C. These are distance between one lattice point to other lattice point along x, y and z direction. So now let us move to next slide, that is Bravais lattice. This is important to understand what is the basic difference between crystal system and Bravais lattice. Crystal system is classification based on only lattice parameters. If we tell where are these lattice points, so not only lattice parameters, also lattice points, then it is Bravais lattice. So we are seeing that cubic is there, tetragonal, orthorhombic, hexagonal, monoclinic, triclinic, tetragonal, all are there. All 7 crystal systems are there. Okay, but apart from this, we are also talking about PIFC. P means what? P means only in the corners we will have lattice points. I means we will have a lattice point inside the body as well as the corner. Okay, face centered means we will have on the faces and we will have lattice point on the corners. C implies two opposite faces. Any two opposite faces we can take, there will be lattice point and on the corner. So opposite faces. If someone asks you and you just write PIFC without mentioning who are this PIFC, it will be not good sign. So we have to tell what is PIFC. You see in cubic 3 possibility, tetragonal 2, orthorhombic 4, trigonal 1, hexagonal 1, monoclinic 2, triclinic again 1, 3, 5, 9, 10, 11, 12, 13, 14. So how many types of Bravais lattice are there? 14. So this is Bravais lattice. It is not only based on lattice parameters, it is also based on lattice points. But crystal system, only lattice parameters. We don't talk about lattice points there. So next lecture, we are going to discuss in details about cubic unit cell. Okay, so cubic means we have to remember A, B, C, all of them are equal. Alpha, beta, gamma, all of them are 90 degree.